Hello friends. So today I am going to solve two problems and these are of binary tree problem and one is from binary search tree problem. So one is Leetcode 110 balanced binary tree. So here you have been given a binary tree and we need to determine if it's a height balanced tree. What does a height balance mean? It means a binary tree in which the left and right subtree of every node differ in height with no more than 1. We need to calculate the left subtree's height and right subtree's height of a node and then see if the difference is always less than equal to 1, then this passes the condition. If not, it's not a balanced binary tree. So let's take an example. So we have a binary tree and what we need to do at each node, we need to calculate its left subtree height and right subtree height, and we need to see the difference between these two is always less than equal to 1. Whenever it is greater than 1, it means it failed the condition and we have to return false. Okay, so let's see this example. So what we need to do, at each node we need to get its left subtree height and its right subtree height and get the absolute difference between these two values and see if it is greater than 1. If it is greater than 1, we need to return false, otherwise it is true. So for example, if I am calculating at root level, the left subtree height is 1 and right subtree height is 2, so 2 minus 1 is equals 1, so it's within the limit, so it passes that condition. Then I will come here and I will check for this node. Left subtree height is 1, right subtree height is 1, 1 minus 1 equals 0. So this is also okay. Same way this is okay because it does not have any child. So left subtree height 0, right subtree height 0. So it's balanced. Same way this is balanced and same way this is balanced. So we will return the answer as true for this one. And for example, if I see this subtree, so I will take the left subtree height, which is 1, 2, 3, and right subtree height is 1. So 3 minus 1 equals 2. So 2 is greater than 1. So we need to return false for this one. And second problem is validate binary search tree. And we all know what is binary search tree. So in binary search tree, each node has a property that its left subtree or left node will have less value than the current node, and right subtree or right node will have greater values than this node value. So we have to make sure this condition is followed at each level. So for example, in this example, we only have 3 nodes. Root node is 2 and left node is 1, so it is less than 2, and right node is 3, it is greater than 2, so it satisfies binary search tree condition. So this is a true. But if I come here, if I check at this root level, left is 1, which is less than 5, so it is left tree is okay, and right node is 4 and which is less than 5, so it should not happen, right? So 4 should be left to 5, so this is a false. Okay, now let's solve these two problems one by one. So let's take this example, and here I am solving the problem where we need to see whether this binary tree is height balanced or not. So it means whether the difference between left subtree and right subtree is less than equal to 1. Okay, so how can we solve this problem? So there are two basically approaches, and one is pretty simple, and let me go through that first, and then we will see how we can optimize this approach. So first is simple. We start at the root level and we create a simple function get height of a tree, and we first pass the left subtree and then we pass the right subtree, and whenever we get both values we subtract them, and we see whether that value is greater than 1. If it's greater than 1, we will simply return false, else we will return true. So for example, here I will check the left subtree height, so it will come as 2, and right subtree height will come as 1, 2, 3, 4. So 4 minus 2 is greater than 1, so we can simply return false. So let's take another example. If I use the same approach there, so for example, I will, for this root node, first I will calculate the left height and then I will calculate the right height. So for example, here left height is 1, 2, 3, 4 and right height is 1, 2, 3. So this is equal to 1, so it's a height balanced at root. Then we need to call the same function for left subtree, and we'll come here and again we'll calculate the left subtree, which is 1, 2, 3, and right subtree height is 1. So 3 minus 1, 2, so it's greater than 1, so we need to return false. So in case any of the node is not height balanced, it means that complete tree is not height balanced, so we have to return false. But if you see carefully what we did, okay, so now let's understand what is a drawback in this algorithm. So we have a function get height, and what we did for root level, we called it 2 times for left subtree and right subtree. So basically if it's a log n calling for each side. And now let's try to understand what is the drawback with the first approach. So as you see, first we called get height function to the left subtree of root node and get height function to the right subtree of this root node, and it returns basically 4 and 3 respectively, and it satisfied the height balance condition. Then we went to the left node and then we are calling get height again. So if you see, it's a duplicate work. So first we called the get height for the root node, for this is left child, and we went ahead and calculated the height, and we are doing the same thing now again. So we came here when we are running for left subtree, again we are calling get height for its left subtree and right subtree. So it means we are again doing the same thing to find the so we are traversing all the below nodes of 2 to find the left height, all the below nodes of 2 of the right side to find the right height. And that's what same we did when we were calculating the left subtree height for root node. So it's a redundant thing, and time we go on the left side, we are going log n times, and we are doing the same for all the nodes, so it becomes n log n complexity problem. But what is the other approach what we can do? So what we can do, at the same time when we are traversing get height function for this root node, we can simply check whether each node is height balanced or not. As soon as we find a node which is not height balanced, we can return some value, and based on that the parent function will return that value to the final calling function. So for example, if I call get height function for this node, I will come here, I will come here, I will come here, I will come at this node and see, okay, so it's height balanced because left child and right child height is 0 and 0. So then it will pass something to here and it will check, okay, left height is 1, right height is 0, again it's height balanced. Then it will come to this node and it will see, okay, all the previous nodes are height balanced, and now I have to check. So the length of left subtree is 2 and right subtree is 0, so it is not height balanced. So from here anyway our condition fails, and we can simply return some values to its parent, some value to its parent, so that we don't traverse the tree again. Then it will become order of n problem. So we'll solve this problem and we'll write code for both of this condition, then you will understand like what I was trying to say. But basically it will reduce, the second approach will reduce the time complexity from order of n log n to order of n. So let's go ahead and solve this problem first. Okay, so I am at this problem balanced binary tree, and let's solve this with first approach. And the first approach is very simple. So we will do one thing. First we'll write a function to get height. So I will write it as private int get height, and it will need one node, we'll call it as a root or node. And first, if base condition, if root equals to null, you can simply return 0, so that tree's height is 0. So how we calculate the height of this root node? So first we will call get height for left tree and then get height for right tree. So when I will call get height for left tree of root node, so it means I am passing here 9, this node, and then it should calculate the left height and right height, and whichever is maximum it should pass that value to this root node. Same way, when I am calling the right height of this root node, this function will be called for this 20 node, and it will calculate its left height, right height, and whichever is maximum it will pass it to 3. So at each level what we are doing, we are calculating left height, right height, and whichever is maximum we need to pass that as to its parent node. So int left height, and again we'll use the same function get height root dot left, int right height get height root dot right, and we simply need to return maximum of max.max left height comma right height, and we need to add 1 for that level. So for example, if I am here, I ask what is the left height for this node, it will come as 1. What is the right height of this node, it will come as 1. So I will take maximum of those two. In this case it is 1, and then when I am passing the value to it, I need to just add 1 for this root's height. So it will pass maximum of left or right, then plus 1 to its parent. So this function is done. Let's see now what we need to do here. So if anyway in tree, first check if root equals to null, just return true, because if it's an empty empty tree, it's basically a balanced binary. Okay, now what I need to first get the left height of this node. So I will call get height function for root dot left, and I will call get height function for right node. That's the thing which we discussed, right? So for this node, now what I am doing, I am calling its left child and asking what is your height. I am calling its right height and what is your height, and these two functions will give this parent node, root node, what is the left height and right height. Once I have these two value, I simply need to do if I need to do the AVS function. It's an absolute value, so in case if the answer, if the subtraction comes negative, it will just take the positive value. If left height minus right height, and we will do absolute if it is greater than 1, so we can simply return false, and then we will stop here. We no need to do anything. But if it is not the case, then we need to call the same function is balanced for its left child and its right child. That's it. I think it should work. Let's try. Okay, okay, it succeeded. Let me submit it, and it is accepted. And before going to second approach, let's discuss its space and time complexity. If you see here, right, for each node, so first I'm calling this function for root node, so I'm going to the left subtree, which is order of log n, going to right subtree, so this function will be called order of log n times, and then I'm going through each node again, so of n log n complexity, time complexity, and space complexity will come basically from these functions. And anyway, this will be, you can say, log n. So how to optimize this? As we discussed, what we can do, whenever we are calculating the height, at the same time we can check whether it's balanced or not. If it is not balanced, we can simply return that this tree is not balanced and we no need to do any other calculation. So how to do that part? So let's do it. Base condition is anyway needed, and I can simply comment these two calls, and also I can comment this call, and I will write a helper function, to helper, because now this function's job is not only to get the height but also at the same time check whether that node is height balanced or not. As soon as it gets a node which is not height balanced, it will return some value, and then we can check this final value in this function, and based on that value we will return either true or false. So let's think that value as integer dot min value. So as soon as we get the integer dot min value at this level, we know this is not height balanced. So what I can do, I can either check if this is integer dot min value, you can simply return false, and if it is not the case, you return true. And let me update this here. So we will call it as helper, and we will be passing it as the root node. If root equals to null, we can simply return 0. That's all right. And we will find left height, and this function is renamed to helper. So helper function is basically doing two things. One, it is finding the left height, or basically one, it is finding the height, and second, it will at the same time check whether that is height balanced or not. So now what we can do, as soon as we get the left height value, we will check if this left height equals integer dot min value. If left height comes as integer dot min value, we return integer dot min value to its parent, so telling that I am not height balanced, and you can simply use this value to return to your parent. So we will not do any calculation. Same way, if right height equals integer dot min value, you can simply return same value to its parent, just to signify that I am not height balanced, so don't do any other calculation and just simply return min value to your parent. Okay, and now what we will do, if this is not the case, so your left height is not equal to integer dot min value, your right height is not equal to integer dot min value, then you will simply check same way what we were checking, if math dot abs, so this is the part which we are doing as part of helper function. If math dot abs left height minus right height greater than equals 1, it means then you will simply send integer dot min value. It means that I am returning integer dot min value, so it says to its parent that I am not height balanced, so it means complete tree is not height balanced, so you no need to again find your left height and right height, simply return integer dot min value to your parent. So that part is we are doing here, and at the end, if this is not the case, if left height and right height is less than equal to 1, then you simply return mat dot max left height right height plus 1. Okay, it seems confusing, but it's pretty simple. I want you to go and watch my previous video in order to understand how these temporary or how these intermediate nodes send value back to its parents. Okay, so what we did, this function is doing two things. First, it is calculating left height and right height, and at the same time it is calculating whether that node is height balanced or not. And if it is not height balanced, it is passing some value to its parent. Otherwise, it is creating that value and it is passing to its parent. So let me try to run code. Okay, so it's accepted. Again, now the time complexity will become as order of n, because I am calling this function helper function for the root, and I am not calling it again and again. And as when I am traversing or creating values for this root, I am at the same time checking at each node level whether it's balanced or not. In case it is not balanced, I am simply passing that value to its parent. And so its time complexity is order of n, because I am only touching any node one time, so it's order of n. And space complexity is order of log n, because I will be either at the left side or at the right side of a node. Now let me go ahead to the second problem. So let's see this example. So here again we have a tree, and we need to validate whether it's a binary search tree or not. So we'll check at the root level. Okay, so its left child is 50, which is value is less than the 100. Okay, that satisfies the binary search trees criteria, so it's okay. And I check right child of this root node, which is greater than this root node's value. Okay, this satisfies that condition of binary search tree. Then again we'll call the same function for this node and this node, and when I will come to this node, I'll see, okay, the left subtree is less than 25, but left subtree is less than 25. It satisfied binary search tree problem, and right subtree is also greater than this node's value. So it's for this node, it satisfied binary search tree problem. But is this really a binary search tree? So if you see, it is not a binary search tree, because this 125 is greater than root node 100, but again it is on the left side. So we cannot just check one left child and one right child for a corresponding node or root node and say whether it's a binary search tree satisfied property at this node, and simply go ahead and check at each level, because you can get the false answers where each node is satisfying that condition of binary search tree, but complete tree is not satisfying the condition. So what approach we will take is like, we will define the minimum and maximum value of binary search. We'll take both as null. So now I need to define two things. So for this root node, what values can left subtree have? It can have from min value to this node's value, min to 100. And same way, we need to define what a max value can its right subtree have. So it can have from node value to max value. Okay, so let's take an example. So when I am at this root level, what I will do, I will check whether this node's value is in between its min and max range. So initially min and max will be null and null. Okay, at root level, this min value will be null and max value will be null. So what does it mean? That there is no minimum value or maximum value for this root node, so we can have any value, so we are all right for this node. Then we'll call the same function to this left subtree, and we will update the max value as 100 and min value will become as null only, because when we are going to the left, only condition is like the left subtree should not have value greater than this node's value. And again we'll come to this node and we'll check, okay, so if this value is in between the value passed by its parent, so yeah, 50 is in between null and 100, then we are good. And then when we are calling the same function to its left subtree, again we will update the min and max value. Again, if we are going to left of any tree, so we will have left value unchanged and max value will be replaced by its value. So for this node, this will pass null and 50 and it will satisfy this problem, then we are all okay. And when we are passing same function to this right node, we will pass, so from this level for left we pass this, for right what will pass. Now for the right level you have the max value as 100 and min value will become 50, so right node cannot be less than 50 and this 100 is anyway passed from this parent. So at the each level, based on the left or right node, we have to update these values. So I will pass 50 and 100 and I will check whether this value is in between these two ranges. So it is not. So as soon as I come into this level, I simply pass false and this complete binary search tree validation will go false. Okay, so let's start. So as with all tree problems, first you check if root equals null, and in most of the cases if it is null, it means it's a true condition. Anyway, for this condition it is true. If there is no tree or root is null, it means root is null. It's a valid binary search tree. Then what I need to, I will use a helper function and I will call it as helper. I will pass root value, and as discussed we will pass null for min and null for max value, and whatever that function returns will simply return that answer. Here that function should also return boolean, because main answer is in boolean and we are simply returning the value whatever is being passed from the helper function. So it's again helper will return boolean, and first parameter is root, and here I can take this integer object for min and integer object for max, because they can be null. If I take int, for example this int, it cannot take null values, so I need to take a object variable here, so that's why I took integer for min and integer for max. Okay, so what I want to do, again base condition, if root equals null, you no need to do anything, you can simply return true. So once this base condition is done, what we will check whether that node's value is in between min and max, and if those min or max is null, then there is no limit, so you no need to check that boundary. If min is null, you no need to check the min boundary, and if max is null, you no need to check the max boundary. Okay, so let's take this example. We passed 5 as part of this helper function and we wrote the base condition, and then we are checking whether this 5 value is as part of the limit or not. So first I need to check its min value, but if min not equals to null, then only I need to check, because if min equals to null, it means there is no limit for the min side, so you can have any value for the min. So for this example, when I am running this for 5, anyway min will be null, so we won't check this condition, but we have to write, because when this 5 will call for its left subtree, the min will become min will be null. Okay, when I will call this function will be called for its right subtree, min will become 5. So that's where we can have if min not equal to null, and then this root's value is less than equal to min, we can simply return false, because it should not be less than or equal to min. And at the same time we'll check for max. If max not equals to null, and root dot val is greater than or equal to max, then you will again return false. So I hope you understand, because greater than max, so root dot value should always in between min and max, and not even be equal to that min and max value. So if I come here and if I read this condition, the left subtree of a node contains only nodes with keys less than the nodes value. So left should always be less than the nodes value. The left cannot have the value of nodes. So for example, this left cannot have 5 here, because this, as part of this condition, this left should always be less than the nodes value. So whenever I have min value, I need to make sure that roots value is not even equal to that min, because as part of these two condition, the left node should always have value less than the nodes value, and right should have always greater than nodes value. So to check that condition, we have equal to condition also here, and if these two are not satisfied, then it means this node satisfied binary search tree criteria. Now I simply need to call this function to its left and right subtree. So, and whenever I am passing any value to left subtree, so for this example, the min is again boundless, so you can have any min. So whatever min its parent has, we need to simply pass that min value, but max we need to pass it roots value, because the left side cannot be greater than or equal to this 5. So I will pass it here root dot val, and at the same time I need to check for this right subtree, and for right subtree what will be the range. So min will be updated to 5, but max again will be boundless whenever I am calling for that right subtree. So helper root dot right, and min is root dot val, and max is whatever that node has the max value. Okay, let me try it. Okay, let me submit it. Okay, it is done. Okay, so let's discuss what is the time and space complexity for this problem. So the time complexity will be order of n, because if you see, this helper function is only called once from this main parent only for this root, and at each level you are calling either for left subtree, means for left subtree and right subtree, and they can, and so it means we are only traversing once all the nodes, so it's order of n. And time space complexity will be only because of these stacks memory created by this helper function, because as if you see, we are only using two variable min and max, and they are order of 1, and stack memory can be log n times. So because for this node we will first call everything for the left hand side, and for a balance tree it will be log n node on the left of this side, so it will be log n, and once it is complete left subtree is done, then only we are calling for right subtree, so that will be again log n. So those are separate. So it means the space complexity is order of log n, that too because of this function call. So that's it, friends. I hope you like this video, and please subscribe and like and share this video. I'm thinking to start now some dynamic programming problems. Hope to see you soon. Thank you. Bye.